So you'll remember that we did these notes a few days back, and we got about halfway through them before we went to see Mr. Smigalski's class drops and stuff. I briefly talked to you about Newton, how it was quite likely that the apple did not actually hit him on the head, but he likely saw an apple fall, and at the same time saw the moon in the daylight traveling across the sky, and wondered if it was the same force, and of course it was. And this led him to the law of universal gravitation, which basically says there's a force of attraction between everything, or every two things, and this force is proportional to the product of their masses and inversely proportional to the square of the distance between their centers. And as a actual formula, it looks like that. F equals big G m1 m2 all over r squared. This is not a formula that you need to worry about. You will not have any word problems associated with it in grade 11. You will, however, see it in grade 12. All you really need to know is that this force exists between objects, and it's actually quite tiny, and it's very much dependent upon their masses. The force of attraction between me and the filing cabinet is relatively small because of our relatively small masses. The force of attraction between the Earth, Peyton, and the filing cabinet is large because the Earth is large. Jake.
Is the force still measured in newtons?
Yes, it is. So the combined masses of the two are what determines the strength of it. It's also inversely proportional to the square of the distance between their centers. If I stand 1 meter away from the filing cabinet, and then I stand 2 meters away from the filing cabinet, that force of attraction is now 1/4. And how did you get 1/4, Keelan? Twice as far, but it's the r squared, so the 2 is on the bottom. Squared, 2 squared is 4, so in fact I'm 1/4 of the attraction to the filing cabinet. If I'm 3 meters away and I'm now 3 times farther, I'm now 1/9. Inverse square law. A lot of things are proportional to this inverse square kind of thing. Light, if you get twice as far away from a light, the light intensity is 1/4. Sound, same thing. Every doubling you do, it's 1/4 the intensity of sound. So lots of things relate to that 1/4. And you'll see them in your future physics careers. I think we left off, I was trying to come up with the value for G, wasn't I? I think I quoted, yeah, I quoted 6.67 times 10 to the minus 31. It's a very tiny number. Come on, go to the next page. Here we go. So the region around a mass in which a second mass will experience a gravitational force is described as a gravitational field. And we saw that in the handout yesterday, and I know there's a picture coming, so why are you drawing it? It should be right down here, I think. Come on. There it is, right? So the strength of the field at any place is defined as the gravitational force that a unit mass. We use 1 kilogram as the standard mass. The gravitational force, the strength of the field is how much force 1 kilogram would experience. On Earth, it's 9.8. 9.8 what? 9.8 newtons per kilo, right? It's 1 kilogram, it would receive 9.8 newtons. That is the gravitational field strength of the Earth. This field strength is represented by a small g. When a gravitational field is drawn, the field lines are closer together where it is strong, and where it's weaker, they are farther apart. So here, close to the Earth, where the lines are close, right, it's stronger, and up here, where they're farther apart, it's weaker, but still existing. Now, we got to here, I remember, this diagram implies that gravity is weaker as you climb an altitude. We know that. If I were to graph gravity at different altitudes, it would look like this. It would be that inverse graph that we saw in Unit 1, right? And this particular point right here is about 400 kilometers up, which is about where space shuttles orbit. And there's a note here on the side that says, notice that at an altitude of 400 kilometers, gravity still pulls at about 9.5 newtons per kilogram. So every astronaut is experiencing a gravitational field strength of about 9.5 newtons per kilogram. The International Space Station, a little higher than 400 kilometers, I think. Aren't these space shuttle astronauts experiencing weightlessness? Now, I've talked about this, so you should know the answer already. Are they experiencing weightlessness? Apparent weightlessness, and why is that? And here's the diagram that really sort of makes it make sense for kids. The space shuttle astronauts and everything else in orbit are actually falling forever. When I tried to drop the scale, I could only drop it so far before my arm gave out, and then I had to actually hang on to it, right? And even if you were to jump off the seniors high-rise downtown, you would only fall for maybe a few seconds. When we saw Felix Baumgartner jump off the big Rio Jesus statue yesterday, how long did he fall for? Well, not very long before he pulled the parachute, right?
Yeah.
Even when he jumped from the edge of space, he fell for like about 3 minutes or so, right? He experienced weightlessness for like 3 minutes. But if you're in orbit, you are actually falling forever. Now, how does this work? Remember the day when I threw the cup over Zach's head?
No.
Remember that day?
I wasn't there.
Maybe you weren't here. It was a lot of fun. I dumped a big thing of ice water on Zach's head.
Did it actually fall? No. You're just throwing
The thing is that they never land. Why do they never land? Because the shuttle's traveling at a great horizontal speed. Now, if you add these vectors graphically, and what you should do is just watch right here, right? The shuttle is traveling horizontally sideways because it's an object in motion, and we know that objects in motion stay in motion. Does it need to keep the thrusters on?
Nope.
No. Once the thrusters have pushed it, right, at a certain speed, it just keeps on giving her. Now, Newton also said that it travels in a straight line forever and ever. Why then does it orbit? Because of gravity. Gravity is pulling it in, right? And so it's actually falling down and falling sideways at the same time. What do you know that falls sideways and down at the same time? Bradley's got good hands. I'm going to throw the tennis ball to Brad. Good hands. Did the tennis ball travel sideways?
Yeah.
It certainly did. Would it also fall as it went? It sure did. Throw it back, and you'll see the arc, right? You'll see the arc. Why is it doing that? Because it's going that way and also that way at the same time, right? Do you remember? Did I do the thing where I walked down the thing and then? Yeah, I did that, right?
Yeah.
Yes, I did.
What are you talking about?
You're a bad kid, Baruch.
What are we doing?
I'm talking about if you guys stood on the side and watched, as I walk like this and throw the ball up in the air,
Nope.
what does it do?
Nothing.
It actually travels in an arc, lands right in my hand, doesn't it? Remember that? Bad words.
No, I said I go up your backwards or something.
You mean like this?
Yep.
Yeah, you actually have to throw it straight up, right? I come in and I practice on the weekends, kind of. If I walk at a constant speed, throw the ball straight up. Oh, that was a bad throw. The ball actually does what? On the side, you would see it doing what? Arcing, right? I don't see it because I can see it going up and down because I'm traveling sideways, right? Same idea here. But when I get to the end there where Liam's sitting, the ball lands in my hand and that's the end of it. But if I could walk fast enough that I would be like sort of around the corner of the curvature of the Earth, where would I fall to? Right? When I add that vector and that vector together, I get something like that. Well, guess what? I'm still being pulled that way. And which way is it going? Sideways. And so now I add those together, and where do I end up going? Like that. And what happens? Well, I'm also being pulled down, and I'm also traveling sideways. And so where do I end up going? Like that. And I continue to add the vectors, and what happens? I am in orbit. I am continually moving straight forward in a straight line. I am continuing to fall at the same rate.
So that like if you like jumped off the Earth, you like would just keep going around or what?
And actually there's a lot of old physics textbooks have this diagram. If you imagine a really tall building on the Earth, okay, there's a big seniors high-rise, right? And I go and I stand at the top, and I fire that tennis ball, fire it like this, right? Well, if I just sort of toss it off the building, what does it do? Whoops.
Don't tell me you would just wait and turn around and it would just...
It would, if I just tossed it, it would go like this. But if I really fired it, would go like that. But if I really, really fired it, would go like that. If I really, really, really fired it, would go
all the way around.
all the way around and hit me in the head. In fact, if you could get rid of air resistance, and I had a cannon for an arm, I could theoretically throw the tennis ball hard enough that it would just go all the way around the Earth, about 3 feet off the Earth, right? Hit me in the head about 90 minutes later.
Sick.
Let's try it, yeah. Catch. Okay? That's why things orbit. They are continuing to move forward. They are continuing to fall. And when they have reached the point where they should have hit the Earth, right? When they reach the point where they should have hit the Earth's no longer there because of the curvature of the Earth. And so it simply just continues to fall all the way around. Free fall. And when you are in free fall, you are in a state of apparent weightlessness. Are you free from gravity? No. The average person on the street doesn't understand this. You are an exclusive bunch. If you ask the average person on the street, they think that the astronauts are experiencing weightlessness because there's no gravity there. There has to be. If there was no gravity there, what would they do? They would fire away in a straight line and never come back. That would be bad. It's gravity that keeps them in orbit. Make sense? The vector sum of the horizontal motion and gravity causes the shuttle to orbit the Earth at high speed. Since gravity is constantly pulling down on the astronauts, they are in constant free fall, which is apparent weightlessness. They actually do have a weight, they just can't be measured. If we take my Newton scale up there, will we find a weight on them?
No.
No. Okay, because there's no support force. Okay. Here's a little discussion about weight, which I've sort of touched on already in handouts. An object's weight is simply a measure of the force of gravity on the object at that particular instant. Since weight is a force, gravity is acceleration, therefore, and I know you've seen this already, Fw equals mg. We've seen that in previous units, right? Weight force, mass times gravity. Fw is the weight, m is the mass, g is the gravitational field strength, which of course on Earth is 9.8. On the moon it happens to be 1.6. I don't know all the other planets, sorry.
Okay.
Yeah, you'll forgive me, right?
Yeah.
The greater the mass, the greater the weight, since g remains constant. Right? A larger person, if they jumped on my Newton scale, would weigh more than 800 newtons. A smaller person would weigh less on this. Okay?
Is our moon like the biggest moon, or why is it so special?
No, our moon, because it's ours.
Yeah, but all the other moons.
All the cool kids are going there, right?
Yeah.
Actually, there are moons of Jupiter that are the same size as Earth, I believe. That's how big they are, yeah.
Oh, it's on this thing.
And why would they want to go to our
Oh,
moon?
whatever. How,
It's closer. Say again, Hannah?
how, like, there was this, like, info, I don't know where it was, but this thing of how small Earth really is and all the other planets.
Yeah.
Earth was huge and one of them kept getting smaller and smaller, and all the ones that were ginormous compared to Earth were, like, teeny, for just one.
I have a video that I show like that in grade 12. Yeah.
Can you watch it here alone?
I can watch it right now.
Are we that special?
For example, when you stand on a bathroom scale, the scale reads the amount of force that you are exerting on it due to gravity, converts it to mass unit. It's just calibrated in kilograms or pounds, right? It can be calibrated in newtons. It can be calibrated in any other force, any other unit you want. Really. If you want to make up your own unit, go ahead. It's just a little tiny mark on a dial. That's all it is, right? Remember that Newton's law says that there's an equal and opposite reaction force. The scale experiences an upward force, exerts an upward force on you. This upward force is known as the normal force, and we've talked about that previously. And it always opposes gravity, right? Here's a gentleman wearing suspenders on an elevator with a bathroom scale. Yeah, wearing yellow pants. Suppose you took that scale onto an accelerating elevator. You ride the elevator while standing on the scale. Since the elevator and thus the scale are accelerating you up in the air, there's an acceleration that must be applying a force, a greater normal force on you. Since you must react with an equal and opposite force to keep Newton happy, you appear to weigh more because the scale doesn't know the difference between riding in an elevator and a person with a greater gravitational pull, right? All it knows is how much force is being pushed on it. And if the elevator is pushing up to accelerate you up, you must therefore push down more to keep Newton happy. Therefore, the scale reads a greater amount.
Would it be like a lock grader, or would it be just like?
It depends on the acceleration. If it's just a little bit of acceleration, it would be locked. If it was like
the CN Tower.
yeah, like, for example, if you're a test pilot in a plane, right, and they, punch the thrusters and you accelerate at greater than 9.8 meters per second squared, you are experiencing what kind of force?
Bigger force.
Starts with the letter G.
Gravitational.
It is the letter G, a G force. They talk about pulling like 2 Gs. What does that mean? Twice the pull of gravity. It means you're experiencing gravity of, not 9.8, but 19.6, right? You would feel, if you're experiencing a gravitational pull of 19.6, you would feel twice as heavy. You'd feel like you weigh 400 pounds instead of 200 pounds, right? If you've seen pictures of the test pilots, their face kind of goes, like this, right? Yeah, thank you, Joey. Just like that, exactly. He made a face. Come on, make the face. Joey.
Joey.
Sure, it's all fun to make faces and then when someone wants you to, right? Yeah, exactly. If you're going to ride that elevator down, you would weigh less. Why would you weigh less?
Because you're in apparent weightless position.
Well, there's no more. If I'm riding on my scale down in an elevator, like right now when I'm standing at the top of the building on my scale, gravity's pulling me at 9.8, right? But when the elevator drops away, what kind of support force do I need? None or less. Certainly less. Maybe none, right? Probably not none. None would be bad. Yes, you would want some support force, but it might be less support force, and so you just naturally fall, so does the scale. Scale reads less. It's pretty simple, really.
Can we watch that video now with Mythbusters?
We won't get to that one, no. I'll save that one. Yes, he's pretty much devoted to just watching TV.